with the talk of Bohdan Ivanovich Kopytko and Roman Shevchuk from Czestochowa University of Technology and Lviv Polytechnic University on Feller semigroups for one-dimensional diffusion process with moving membranes. Okay, please.
Thank you very much. The report is devoted to the study of the following two questions. Establishment of the classical solvability of the certain non-local conjugation problem for a linear one-dimensional parabolic equation of the second order with discontinuous coefficients, and construction using the solution of this problem of the two-parameter Feller semigroup associated with some inhomogeneous Markov process on the line. The union of these two questions represents the so-called problem on pasting together two diffusion processes on a line, or the problem on construction of the mathematical model of the physical phenomenon of diffusion in medium with membrane. This problem was formulated by Bohdan and Kopytko. So let us consider the strip ST, which is separated into two domains, ST1 and ST2, by the continuous curve x equals h of s. Denote by d1s the interval from -infinity to h of s, and by d2s the interval from h of s to plus infinity, and let ds be the union of d1s and d2s. We also need the set dis delta. Here delta is any positive number, and ds delta is the union of d1s delta and d2s delta. In the strip ST, we consider two uniformly parabolic operators with bounded continuous coefficients. The problem is to find a classical solution of equation 2, which satisfies the initial condition 3, and two conjugation conditions 4 and 5. Here, the function phi is bounded and continuous on the line R. The functions q1 and q2 are continuous on the closed interval 0 t, and furthermore q1 and q2 are non-negative, and their sum is positive for every s. The measure mu is a non-negative Borel measure on ds, such that for any delta which is positive, the inequality 6 holds. We can see that inequality 6 allows the measure mu to be infinite. Note that the problem, the formulated problem, appears in the theory of diffusion processes when constructing the one-dimensional model of diffusion with membrane, or when solving the problem on pasting together two diffusion processes. Here, in the case of in the case under consideration, the membrane is placed at point H of S. This is the point of pasting together two diffusion processes. We prove that there exists a unique solution of the problem 2.5, and that the family of operators, here it is, TST phi of x, which is the solution of the this problem. We prove that this family of operators is the two-parameter Fowler semigroup associated with an inhomogeneous Markov process on the line. The fulfillment of equation 2 for the function TST phi of x means that this process coincides in DIS with the diffusion process given there by the generating operator LSI. And this is the condition 4 reflects the Fowler property of the process, and the condition 5 is a kind of general Fowler-Wenzel conjugation condition. The general Fowler-Wenzel conjugation condition has the form, here it is. It has two more terms, the term with the unknown function and its derivative with respect to the time variable. In our case, the function R, the function gamma equals 0 for all s, and Q1s plus Q2s is positive for every s.
Excuse me, I have a question relatively to this idea that function r is equal to 0. Is it connected that in this case, if we input this function r, then we need some regularity from function h, which is vector?
Yes, we need yes, of course. But today I will report on the case when there are no the term of this function r. Yes. Of course, we have results in case when the Fowler-Wenzel conjugation condition contains this term. We also have results when there is only integral term in Fowler-Wenzel conjugation condition, but it's a pity, but we can't solve the problem in this case when the measure mu is infinite. We only can solve the problem when the measure mu is finite. And in this case, we can allow the measure mu to be infinite, but the inequality 6 must be satisfied. Here are some additional conditions on coefficients BI and AI. The equation, the parabolic equation, the coefficients of the parabolic equation exist. There exist positive constants b small and b large, such that this inequality holds. The coefficients, the diffusion characteristics AI and BI are continuous in the closure of ST, and belong to the Hölder class. Here it is. We need additional condition on the measure mu. This condition that for any function f and any number delta, such integrals are continuous on the closed interval 0t as functions of s. We also need the condition on the function h of s. It is continuous and belongs to the Hölder class with exponent 1/2 plus alpha half on the closed interval 0t. In order to solve the problem, it is convenient for us to write the function u in the form 7 and to rewrite the conjugation conditions 4 and 5 in such a way. Solution u of s xt equals ui s xt of problem 2.5 has the form of a sum of the Poisson potential and the simple wire potential. Here gi is the fundamental solution of the corresponding parabolic equation. And densities vi are determined as the solution of some system of Volterra integral equations of the second kind. To solve the problem, we also need the theorem on the we use the theorem on the jump of the conormal derivative of the simple wire potential. From this theorem, it follows that if the curve h of s belongs to the class to the Hölder class with exponent 1/2 plus alpha half, for some alpha which is in the interval from 0 to 1, and the function vi is continuous and satisfies in this domain the inequality, here it is, then the function ui1 satisfies the relation 9. We also need to use the Holmgren transform. Here it is. And this transform allows us to reduce the system of Volterra integral equations of the we will have the system of Volterra integral equations, and there are some equations of Volterra of the first kind, and we reduce them to Volterra integral equations of the second kind using this transform. Here it is written the system of Volterra integral equation of the second kind for the unknown functions vi. And we have large expressions for functions psi and kernels nij here, but I want to consider only one term, which is a part of the large expression for kernels Nij, because we have some problems with this term. It doesn't have a weak singularity. So when we tried to estimate it, we obtained the inequality 13. All other terms in the expression for kernels Nij admit the inequality with the right-hand side tau minus s to the power of -1 plus alpha half. Here there is some positive constant. But this one integral causes problems because the inequality 13 doesn't allow us to use a method of successive approximations for this system. Concerning a function psi, we obtain the inequality 12. And despite this strong singularity of kernels Nij, we can prove that the method of successive approximations can be applied to the system, and the function Vi can be found in the form of series 14, where Vi0 equals function psi, and the other terms of this series are defined by these formulas. And this is the main part of our research, to prove that we can use here the method of successive approximations. And so I want to explain, I want to try to explain why we can use this method here. I want to estimate, to show how we estimate Vi1. So consider this bad term, and we can only consider this term when you see here we have integral over djs, and we can only consider this term when we have the integral over djs delta, and here we can write the main part of the fundamental solution gj. So here is this integral, and we write it in the form 15. Then we take the derivative with respect to theta, and I want to note also that the derivative of this expression can be written in this form. So we will have two terms for the integral ij. Here they are, ij1 plus ij2. Here the term ij1 admits a big singularity, admits inequality 17, and we can represent the kernels Nij as a sum. This bad term without weak singularity Nij2, and all the rest terms, the rest of expression for Nij, which admit the inequality 19. The terms with this integral can be estimated using the fact that using the simple inequalities 21 and 22, we can construct estimate 23 for Nij2. Here it is. Now we can estimate Vi1. To do this, we have to apply the relations. This integral, we can take this integral, and the inequality 6. The inequality 6 are the conditions, is the condition on the measure mu. Also, I want to say, okay, about this, where here it is, about this integral, why we have inequality 17 for this integral, because the function h is Hilbert continuous, and here we can use to estimate this term the Hilbert continuity of function h. So here we have the estimation for Vi1. We can write it in the form 24. Here, delta can be chosen so small such that this term m of delta is less than 1. We fix such delta and put let C be the constant C of delta when delta is fixed, and the same is for M0. And we obtain, using the method of mathematical induction, we obtain the inequality 25 for the general term in the series. So our main result can be formulated in the form of theorem 1. The non-local parabolic conjugation problem 2.5 has the unique classical solution continuous in the closure of ST. Furthermore, this solution has a form of the sum of Poisson and simple wire potentials and satisfies the inequality. Here it is.
Excuse me, where maybe I missed it, but where we state that it is the solution is unique.
we can prove that solution is unique using maximum principle.
But how do we use it? We don't have. We have on initial condition. We haven't fixed a boundary. So how do we apply a maximum principle now?
We proving the uniqueness of a solution of this problem. We consider the theorem on uniqueness for the first boundary value problem. One moment. I have to think. We consider two solutions, U1 and U2, and consider their difference. And the difference can be considered as the solution of some first boundary value problem.
But I don't understand actually what will be a condition at the function s h on this boundary h. What we will have on the boundary, because we have to apply some theorem, yes.
Yes. Maybe maybe I will show you the proof, but I need to switch.
Okay, maybe we can go further and discuss this uniqueness at the end of the seminar. Yeah?
Okay,
because
thank you.
It looks like the most easy way will be followed. That we just say, okay, we have a class of solutions which satisfy such a priori estimation like you get in the theorem. Then in this class of solution, due to applying of iteration method, we have uniqueness because the remaining term will go to the zero.
Yes.
I think that we can do this as follows. If we say that we are looking for the solution that satisfies some a priori estimation, but in general, let us discuss it in the end of the talk. Okay, please go further.
Okay, thank you. Theorem 1 allows us to define the two-parameter family of operators, TST, by using the solution of the problem 2.5. In fact, we can consider the obtained solution as the two-parameter family of operators, and it is the desired operator family. We prove that for these operators hold some properties, properties 1, 4. For example, here we have the semigroup property. The property 3 is the property of the property 3. Non-negativeness is the property of non-negativeness. And the property for here we prove that the operators T as T are contractive, that is that do not increase the norm of element. From the properties 1 4, it follows that the family of operators T as T is the desired semigroup is a semigroup associated with some inhomogeneous Fowler process on R. And if we denote by P its transition function, then T as T phi of x can be represented by the relation 27. By direct calculations, we also can find using this semigroup, we also can find that for any S and for any phi from this class and F, which is real continuous with compact support, the transition function satisfies the relation 28. So this is the generalized infinitesimal generator for the corresponding semigroup. Here we have some relations. If we additionally assume the existence of moments for measure mu, then the second term in this relation can be rewritten in such a way, and considering this relation, we see the influence. We see how the parameters in the Fowler-Wentzel condition influence the diffusion characteristics of the process when the diffusion particle reaches the membrane. Also, using this semigroup, we can find the generalized diffusion coefficients for the constructed process, but only in case when the measure mu is 0. So by direct calculations, we established these relations, which means that in this special case, when mu is 0, the constructed Markov process with the transition probability P can be treated as a generalized diffusion process in the sense of Polytechnic. With a generalized drift coefficient, here it is, and the diffusion coefficient B, where delta of x is the Dirac delta function.
Excuse me. So you said that you can only say that this is generalized diffusion only in a case when mu is totally equal to 0. So if mu has any regularity with respect to S is very good. For example, it can be a delta measure concentrated in one point. It is then you also cannot say that this is generalized diffusion. This is some other process, yeah?
Yes, because we use sufficient condition for here. We can't. Yes, we can prove this assertion only when mu is 0.
But what is the reason why the presence of mu is so bad? Why it causes does it cause the non-existence of the limit, or you cannot prove that the limit
We
exists?
cannot prove.
The process is discontinuous, so that's why probably it cannot be generalized diffusion in this sense.
Yes.
So we can prove that it is discontinuous in this case, or what? Which process, by the way?
I believe that if mu is not 0, then constructed diffusion, constructed Markov process is discontinuous.
So
probably.
mu is like jump or what?
Yes, mu is like jump measure, intensity of jump measure from the membrane.
Okay.
And
okay.
it would be very interesting to construct such processes from excursions. So it seems to me that some excursion comes through the membrane continuously, and some excursion can exit by a jump. But if mu is infinite measure, then it's intensity like Levy measure.
Yes, yes, I understand. Okay, so we cannot choose it in stop. But suppose that it concentrated only on the line, on this function h, yeah.
Assume that h of s is 0. So
yes, so it is constant, yeah.
So we jump from 0, for example. Yes. So we have semi-permeable membrane. So some excursions come, exit, and enter from 0 continuously, and some excursion exit from 0 by a jump. So this is possible.
But as it seems to me that mu describe for us the size of the jumps, yeah.
Yes.
But if mu is concentrated only in 0, then
no, mu cannot be concentrated at this point.
Oh, I see. Then of course, because maybe I forgot the condition. Why mu is not concentrated in one point?
No, it cannot be concentrated at the membrane. Is it correct?
Yes, so, yes.
I see. Okay, so, sorry, I forgot this condition. Yeah. Okay.
Okay.
Yeah.
So.
Roman, and can mu be infinite?
Yes, mu can be infinite, but it must satisfy this condition. And here ds delta is the interval. Here it is. So the mu cannot be concentrated at h of s. Yes.
Yes. Okay. Thank you. Now it is reasonable that when mu is present, then you cannot generalize the diffusion process.
Roman, yeah, I have a question.
Yes.
So, do you have a continuity of a solution depending on measure mu? I mean, you have a semigroup.
Yes.
And assume that you have a sequence of measures mu n that converge in some sense to measure mu.
No, we don't have such assertions. No.
Because it will be interesting if you get some continuity principle. For example, your solution is continuous in H, mu, B, maybe A.
I understand.
And then you can say, okay,
Thank
for
you
example,
for the idea.
if and then you can approximate mu by finite measures. For example, if you prove continuity, and I believe that if mu is finite, then you can describe this process like this.
Sorry, one more time. When mu is finite?
Yes, when mu is finite, I think the process can be constructed in the following way. You construct a process mu is 0, and then calculate the local time on this membrane. And when this local time hits some level, well, I don't know, some exponential maybe level, or then you have a jump, and mu will be like a size of a jump. Well, mu divided by total variation of mu.
Mm-hmm.
Then it will be clear what is the process. However, this may be not trivial too. And then it would be interesting that is it possible to work with infinite mu and have some approximation by processes that have transparent probabilistic structure.
Okay, thank you.
Okay, let's go further, then we continue discussion at the end. Mm-hmm.
We have finally, I want to say that for this semigroup, for this process, we can also determine the ordinary weak infinitesimal generator. This generator, we denoted by AS, is defined on functions, bounded continuous functions, such that here must be 2, such that relations 30 must hold, and for them the operator ES we obtain this relation, and the final theorem is that the two-parameter family of operators TST defined by the corresponding equality as a solution of the corresponding parabolic conjugation problem is a semigroup associated with the inhomogeneous Markov process on R, which transition function P satisfies as a relation. 28 here is this relation. I think it is the end. Thank you for your attention.
Okay, thank you very much. Actually, we began discussion already, and let me recall you that the first question was about uniqueness of the solution in the theorem 1.
Yes, I can show you the proof of the theorem on uniqueness, but I can take another document.
Okay, let's do it. Yeah.
One moment.
Mm-hmm.
Andrei, may I say a few words about the uniqueness?
Exactly, Nikolai Ivanovich. Actually, we have time for discussion, yeah.
If the membrane is unmoving, then the corresponding proof looks like this one. Suppose that we have the following problem. If the initial function phi of x is non-negative, then the solution is also non-negative, we should prove that the constructed solution is non-negative too, as well. Okay? This is the sense of maximum principle. So suppose that phi of x is non-negative and our solution on some time interval takes on negative values. So it is not difficult to understand that the point in space where that minimum attains is the point where membrane is located. It is not difficult because to the left of membrane we have a parabolic equation.
Yes, it's reasonable. Yeah.
Okay, so the negative minimum is attained by the solution only at the membrane, at the point where membrane is located. Okay, and now it is not difficult to comprehend that the derivatives, the right derivative and left derivative have the different sign at this point. Okay, the different. Yeah. But from the equalities, it is not difficult to see that that those derivatives are of the same sign, So these contradictions shows that negative minimum cannot be attained if phi of x is non-negative, if initial function is non-negative. Okay?
Yes.
I think that something like this must be in this situation.
Okay, but as far as I see here, we have some boundary condition, a function j indexed by I, yes, and this j must be calculated, and we have to check something. This is, I think, exactly the analog what you said about the derivatives. Yes.
Repeat, please.
You see, here we have finally boundary value problem 233, 234, and 235. But in the boundary condition 235, you have a new function j, which is calculated. This is, I think, this is derivative. Or what is this? How the function j is calculated?
And there is no dependence on mu, on measure.
Maybe B2 say something for us, but I don't know. Okay, maybe we can leave this question because at least when we have a good estimation for solution, suppose that we have good a priori estimation, then we for free have uniqueness of the solution from iteration method. Also, we already began discussion which is related to probability sense of the solution and to possibility of approximation of the solution. I have the same question, but related to the function h. As far as I remember, when function h is constant, this problem was already discussed, the problem of the construction of such process.
Yes.
Am I right? Yes.
Yes.
Then maybe proceed as follows. Just substitute the function h by the step function using some division of the time interval, and supposing that on every time interval we have different values of h. But of course, the step function will approximate for us the function h what you get. Then, what do you think? Do you have the limit? Do you have the solution or not?
I'm not sure.
Yeah.
Or you can subtract h of s, and then you'll get membrane on 0, but diffusion coefficients and drift will be changed and measure mu.
Yes, yes. And what is interesting for me, this Andrei, about your question of description of the solution due to excursion, that function h, at least in presented result, must be Hölder continuous just more than 1/2. Why? Because I think that if we will discuss the construction with
yes,
excursion,
because regularity of Wiener process is 1/2.
Exactly, because of the law of iterated logarithm. Yeah, we can have a situation when we never hit this h. Yeah, something like this. Yeah.
I have one more question about another alpha stable noise. Assume that you have like fraction Laplacian with alpha between 1 and 2, and consider and assume that membrane is located at 0, and there is no boundary conjugation condition with derivative, but only with measure mu. Maybe you don't have to apply theorems about potential, about single or double layer potential, and just use some iteration and show existence and uniqueness.
But you have to start from something. You have to use some kernels. You see how this transform was useful when you have the a priori estimation of singularities, yeah?
So
that's true.
We can't when the conjugation condition contains only integral term. We can't prove this assertion in case it is infinite.
So when I constructed skew-Levy process, we used resolvent techniques and Ito excursion processes, and it appears that stochastic differential equation for skew-Levy does not contain local time at the point. So the equation was the following. Some differential of a Markov process is equal to differential of Levy process with stable Levy process with alpha between 1 and 2, and then some process of bounded variation taken at the local time. And all failure processes that behave like Levy alpha stable with alpha between alpha with alpha between 1 and 2 everywhere except of 0 satisfies such equation. So du, so fractional generator is fractional Laplacian everywhere, and some boundary condition, but without derivatives at 0. So well, I think that there are no derivatives at 0. And maybe you can consider at first finite measures when you hit 0 and then exit by a finite jump. And then pass to a limit and use some iterations, some estimates for kernels.
Maybe. Thank you for the idea.
Okay, maybe some other questions or comments, please. Okay, if there are no other questions, thank you very much for interesting talk.
Thank you.
And for this seminar, we end our work. Next speaker, I think, will be Nasir Ganihodjaev, yes?
Yes.
Yeah, yes, yeah.
Okay, okay. So, see you next week. Bye.
See you. Okay, bye. Bye.
Bye.
Bye.
Thank you.
До побачення.